Okay, guys, it's 11, yeah, and okay, 20, 19, 20, so people are still coming, good. All right, so let's continue. And again, let's just refresh what we've covered and what I'm planning to discuss today. Again, from the very beginning, we started with laying down the foundation, right, of the Newtonian formalism. Then, as a first point, we moved to a multi-particle system, right? And we adopted basically Newton's second law for a multi-particle system. And then during that adoption, all the internal forces were washed out from the game, right? So if you look at the dynamics of the total linear momentum of the system, rate of change, P dot, P capital, right? That can be changed only by the external forces, right? So that's what we got. And then in an attempt to simplify our life, right, we started wandering around, drifting around the multi-particle system in a search for something interesting. And we ended up with point which we call the center of mass. And once we applied the center of mass point, right, for a multi-particle system, of course, we ended up naturally with what we call the translational motion, right? So which partially describes the motion of the system. Not completely, but partially describes, right? Basically, what is translational motion by our definition? All right, so if you create a fake particle with the total mass of the system, m capital, you remember? If you position it at the center of mass, collect all the external forces acting on the whole system and apply it on that fake particle, and if you basically solve that Newton's second law for that fake particle with those external forces, that trajectory is a translational motion of the system, which is basically translational motion, which is just a basically motion of the center of mass point. So using the center of mass point, we introduce the translational motion of the system, right? Okay, but of course we all know that that description of the motion of the system is not complete, because system can rotate, can spin, can do some stuff, some other stuff, not just translational motion. Right, in order to describe that, we started introducing new tools, right, in order to develop a new toolbox, which can be used to describe rotational motion. And in the previous class, we introduced the angular momentum of a single particle, torque, right, conservation of angular momentum under certain conditions. And then, of course, we went to a multi-particle system, right? Multi-particle system, and we started applying all these new tools, right? So we ended up with the fact that the rate of change of the now total angular momentum of the system, L capital dot, equals to the net external torques acting on the system. Again, net internal torque of the system is 0. Right, so basically all the internal torques cancel each other out, and they are not capable of changing the total angular momentum of the whole system, right? So that's where we ended up in the previous class, right? So we ended up with these where are my markers here. We ended up with this. Right? So the rate of change of the total linear angular momentum, total angular momentum, equals to the net external torque acting on this system, right? It's basically like a rotational Newton's second law, which we introduced for a single particle, for a point mass. Now it's a rotational Newton's second law, I can say, adopted or applied for a multi-particle system. And again, you see all the internal torques disappeared. Right? Okay, so now, and we know the amazing properties of the center of mass when we applied for multi-particle system, and we ended up with translational motion. Now, let's try to apply center of mass for this in this case. Again, hoping to get something interesting. And also, before we start applying that, let me ask you a few questions, right, in order to see what we're going to get at the end. Look, you solve the problem like this, like a motion of this ball, for example, right? So you throw it, okay, right? So just a motion of the ball, right? So it's a complicated motion, right? Which you all know. You solve plenty of problems like this. I solved plenty of problems like this, right? So complicated motion can be decomposed in two motions. Translational motion of the center of mass under the influence of external force, plus rotational motion about the center of mass. And I have two questions, and for me they seem to be reasonable. First of all, how come that we're describing motion of the same system, of the same object, and we use, looks like, two different reference frames? First, in order to describe translational motion, right? Where is the origin usually, right? Well, you can position, for example, at the initial point. So this is the initial point, right? So you position the origin over here, right? Of course, that reference frame is inertial, and then you describe motion of the ball relative to this reference frame. Banal stuff, right? But then how come that rotational motion is described relative to the center of mass? It looks like we have two reference frames. If you describe motion of the system, you're supposed to describe it using the same reference frame. How come that you have two reference frames, two origins, looks like? It's the first question. The second one. Okay, so this second origin, which is at the center of mass, basically it's sort of like a reference frame. So what can you tell about that reference frame in this case when the ball flies, right, this ballistic motion, right? What can you say about this center of mass point? It accelerates. Of course, in this case, in the case of the ball, it's acceleration due to gravity, g, when it moves up and when it moves down, right? So it looks like our second, that reference frame, second origin, on top of the fact that it's second, it accelerates. How come that we're applying basically rotational Newton's second law here? You know, you solved this problem plenty of times, right? Many times, similar problems. You apply rotational Newton's second law, which you're supposed to apply only in an inertial reference frame. You apply it relative to the point which is accelerating. It sounds like bizarre. Complete nonsense, right? So basically, these two questions. How come that we have, it looks like we have two reference frames, and one of them is a non-inertial reference frame, but we still apply rotational Newton's second law. Bizarre. Okay, so now, in order to clear these questions, we need to dive into that. So we need to introduce center of mass and see what we can get, again, naturally, through mathematically, right? In order to explain that and justify all those steps. Of course, what we've done solving that problem is absolutely correct, but now we need to explain it and justify it, right? And this material actually, it's from chapter 10, right? So sort of I just jumped way ahead, right, in order to explain this, right? So, and let me write this. Let's bring the center of mass into the game. Okay, I will write it here to save space. So let's bring center of mass into this game. This game. Right? And yeah, probably I should say that this is from chapter 10. I think it's 10.1. Okay, probably, yeah, 10.1. Although we're still in chapter 3. Right? Okay, so now, again, multi-particle system. We'll start with the picture. I will probably do it this way. So first our reference frame, which must be, of course, inertial, right? Remember, because we, when we derived this, we use Newton's second law, normal Newton's second law, right? Original from the foundation. And it means if you use that, it means that these results can be only applied, I mean, this formula can be only used relative to inertial reference frame. So it must be inertial. And then let's assume that we have our some multi-particle system, right? Bunch of particles are at end, center of mass, since we want to bring it into this mass. So let's assume that this is, for example, our center of mass point, and of course position of that center of mass can be defined by using R capital. Right? And so let's assume that this is some arbitrary particle alpha. Position of that particle can be described by the position vector r sub alpha, r small. And position of this particle relative to the center of mass can be described by the, let me introduce this vector, r alpha prime. Okay, so now we have again a triangle of vectors. Of course, we can write we can add them up, right? So as a result, what? R alpha will be R capital plus R alpha prime. So as a result, we have R alpha equals to R capital plus R alpha prime. Right. Okay, we can differentiate it once with respect to time, and of course we will end up with the equation which relates velocities, right? So V alpha equals to V capital, it's a velocity of the center of mass point, plus V alpha prime, it's a velocity of the particle alpha relative to the center of mass point, right? Just banal stuff. Right, and so now what? Basically, what does it mean we want to bring the center of mass? We want to write L in terms of center of mass, and this torques, torques, can be torques, right? Again, we want to somehow bring the center of mass over there. So let's start with angular momentum first. And then, of course, we will get this, and then we will differentiate and see what we can get out of that equation. Straightforward, but a little bit messy. So let's start with the total angular momentum. Of course, by definition, it's just a R alpha cross P alpha. Yeah, of course, summation of the whole system. Summation from 1 to n and R alpha, right? And again, I'm writing relative to the inertial reference frame because we cannot use this equation for anything else. It must be written relative to the inertial reference frame. Cross P alpha. Right. Okay, and now let's make this transformations. Okay, so I will write it summation over alpha. Instead of R alpha, it will be R capital plus R alpha prime, right? So it's this, then cross P alpha, it's M alpha, and then instead of V alpha, I will use that. So it's a V plus V alpha prime. Okay, so now we need to carefully open it up and see what are we going to get. So first I will do this. I will take this with that. It will be my term number 1. Then term number 2 will be that and this. So this will be my term number 2. So first one, summation over alpha R crossed with M alpha and V. So that's my first term. Second, I will take these two guys. Plus summation over alpha, now R alpha prime, right, cross M alpha and this last one, V alpha prime. Okay, and now those sort of cross terms. So then I will take which one? So I took that, this, for example, right? No, let me this. No, that will be the last one. Let me take this with that. Yeah, let me take this, guys. So plus, I will move to the next line. So plus summation over alpha, r alpha prime across m alpha v, right? And now this with that, right? So plus summation over alpha r cross m alpha v alpha prime. Okay, so I think I didn't make any mistakes, I hope. Right, okay, so now it is equal to, and you know what? Let me just write separately this and that term. Or maybe, yeah, let me, which way I should write? Okay, I will just open it up here. So it will be this way, m alpha. So this is just a scalar, I can move to this side, right? And crossed it with v. Right. So what's the value of this sum? Basically, this v capital, it's outside of this sum. You know what? I can probably do this. I will remove this bracket, this parenthesis, and put it here. Right. So what's the value of this sum? We used it recently, I think, in a previous class or the class before that, right? If you remember that. You remember when we introduced the center of mass point, right? We picked an arbitrary point, then we moved around in order to make one term in that equation equal. And what was the structure of that term? It was summation of the whole system, m alpha, r alpha prime. And this r alpha, it's a position, it defines position of particles, right, relative to the center of mass. So we were demanding, let's find the spot where this term is was zero, right? So basically, that is the first definition of the center of mass. You remember I told you that I like this definition because I can see the meaning of the center of mass point. But from the practical point of view, it's kind of, not kind of, it is useless. Definition of center of mass, the first one, which we don't use as a definition overall, right? Okay, so that's that is zero. Let me dump this, right? And so that is zero. And then also look at the second term. Okay, to save space, I will just put here semicolon, right, and rewrite the second term. Actually, I don't have to rewrite. No, yeah, I will just rewrite nothing else. And you know what? Let me move the summation, sum. R can be taken outside of the sum. It will be R cross summation of m alpha v alpha prime. Again, what's the value of this sum? Again, that was, I wrote down almost immediately after this, because if you differentiate this with respect to time, definition of center of mass, you will end up with this, which we use occasionally to solve problems, right, to describe some motion relative to the center of mass and so on, right? Again, so it's just a derivative of this, and as a result, this sum is also zero. Right. Okay, so let me remind, it's basically definition of center of mass point, right? Okay, so this and this are zeros, right? So we can dump them, 0, 0. That's why I wanted to write these two terms at the end of this equation, right? Okay, so now that was my sort of explanation. Let me sort of separate. And now let's continue this. All right, so I will continue this line over here. So what's left? R and V, they don't care about this summation, so we'll just get the total mass summation over the whole system, right? So this will give us the total mass. And we will get R. And of course, makes sense, I will keep M mass with the velocity of the center of mass. So we're getting RMV, right? Register of motor vehicles, right? The first term. And the second term, nothing can be done, right? So I will keep mass with that, with the velocity. So plus, in which way I wrote, I think I wrote it down in terms of P. Okay, so summation over alpha from 1 to n over the whole system, R alpha prime cross P alpha prime. So that's our total angular momentum of the system. So once we introduce the center of mass into the game, so now we have two terms. The first one, what is that? It's the fake particle with the total mass, position of the center of mass, moves with the velocity of the center of mass, crossed it with R, so we're getting the angular momentum of the center of mass point relative to the inertial reference frame. Relative to this origin, I can put it, for example, I can write here O, right? Origin O, right? So we can call it as the angular momentum center of mass, right? Angular momentum of the center of mass motion and so on. Then this, what do we have here? Position of the particle relative to the center of mass. Linear momentum of a particle relative to the center of mass. So these terms, and then of course you cross it, right? So it's the angular momentum of particles relative to the center of mass. And if you add them all up, it will be total angular momentum of particles relative to the center of mass. So this is relative to the inertial reference frame, relative to the origin O. This is relative to the center of mass. Right? So it looks like this term doesn't care about the inertial reference frame. It just lives by itself. Okay, let me write. So this, as a result, L can be written as, let me write like LCM sub Cm plus L prime. Right, so this is, probably I will write, yeah, let me just write this way. Angular momentum due to the center of mass motion. Okay, of the center of mass, and of course, relative. Because whenever you write angular momentum, you have to say relative to what? Right? Relative to our origin O, inertial reference frame, that inertial. Right? And L prime, angular momentum of the system relative to the center of mass, right? And so basically, it makes sense to call it internal, because yeah, it's relative to some internal point in the system, right? So internal angular momentum. So which way I wrote it? The internal angular momentum, of course, about the center of mass. Okay, the wrong color. Internal, angular, what I'm doing? Angular momentum relative to the center of mass. Okay, now, before I looked at some simple example, look. When we introduce angular momentum, I told you, right? And of course, you know that angular momentum, the value of the angular momentum depends on the origin, where you position the origin, right? You remember I told you. So if you grab the origin and start moving, right, you can get basically any value of the angular momentum, right? It's nice to have that option. But now, once we split the total angular momentum in these two terms, only this guy, only angular momentum of the center of mass can be changed. If you start moving this origin, yeah, this L sub cm will change its value, right? Because through this R capital. But this guy, internal angular momentum, it just basically doesn't care. Do whatever you feel like doing. I'm not going to change anything. It's basically my intrinsic property. Where are you going to position your reference frame? I don't care. Total internal life. That's why very often it's sort of like this value of this internal momentum is sort of like an intrinsic to the system. So if you want to change that, you need to change the system somehow, right? But we assume that we're not changing the system. We have a system, it's given, we want to describe it. And of course, to describe it, we can change the origin. And once you start changing position of the origin, I know, trying to get something better, right? So you can change only this term. This term will just completely ignore all your efforts. You can do whatever you feel like doing. That's my internal business, right? Okay, so then, what else? Yeah, simple example, right, of this motion of the Earth about around the Sun, right? So of course, you know, we have two types of motion, right? So we have annual motion around the Sun plus daily rotations about the axis of rotation of the Earth, right? So those annual rotation about the Sun can be described using what? Angular momentum of the center of mass. So you take basically you create a fake particle of the Earth at the center of mass point of the Earth, right? And it spins, right? The origin, of course, inertial reference frame is at the Sun, right? And so that motion can be described using this angular momentum of the center of mass. But of course, at the same time, we have the spinning of the Earth around the axis of rotation, right? That's the internal. Or we can call it spin angular momentum, right? That's why spin is basically an intrinsic property of an object. Even in quantum mechanics, electron, right? Spin of an electron, intrinsic property, right? Okay, so let me draw some quickly solar system in order to tell you that, because in that case, this can be called like a orbital angular momentum, and this is, yes, spin angular momentum. What should I write? Before, let me also write at least one sentence about the fact once you start moving the origin, right, so you can change this term, but you will never change that. And of course, sooner or later, you can find the sweet spot, and this term, for example, can be zero. So all the time, you can find the position of the origin, and you can make this term zero, but you will never make this zero unless you change the system, right? So by moving the origin, you will never make the spin angular momentum zero. Right. So let me write that no change in coordinate system can eliminate spin, or internal angular momentum can eliminate the internal angular momentum. Oh, of course, as I said, unless you change the system, right? But we assume that system is given, and in general, in the most general case, the angular momentum internal is not zero. The internal angular momentum. So, example where this can be useful, as I said, description of the Earth orbiting around the Earth. I mean around the Sun. The Earth around the Sun Right, so I can draw an ellipse, right? So this is the sun. Of course, the inertial reference frame we usually position at the place of the sun, right? And let's say the Earth is here, right? So the orbital motion can be described using LCM. By L sub Cm, orbital motion, right? And the spin motion, it's a daily revolutions about the axis of rotations, right? So that can be, that's spin, right? So which is L prime, right? Internal angular momentum of the Earth, right? Okay, and I can write this also. So daily Earth rotations, daily Earth rotations, that's spin angular momentum, Earth spin angular momentum, spin angular momentum, and of course the annual rotation, I mean the annual rotations. Okay, revolutions. That's the Earth orbital angular momentum. Earth orbital angular momentum. About the sun, of course. Orbital angular momentum. Of course, about the sun, because that's where we position the inertial reference frame. Okay, so we just introduced the center of mass and split only L. So now we know that there are two L's, of the center of mass and about the center of mass. And so now, next, okay, in applications, I think I mentioned everything. Let me just quickly scan again to make sure that I didn't change anything. Right. Again, of course, remember that position of O can only affect this angular momentum of the center of mass. Yeah, it looks like everything. So now, the second, what about torque? Let's again split torque into two terms. So I will put a new big bullet, right? And now torque. So what can be done with that? Okay, so now again, just from definition, right? So we know, in previous class we wrote it down. So external torque equals summation of the whole system, right? And again, relative to the origin O, relative to the inertial reference frame, right? That's how we derive this equation. So it must be R alpha crossed with external force acting on each particular particle, right? So R alpha crossed with F. I think I use upper script. Let me check just quickly. Yeah, alpha external. Okay, again, so instead of R alpha, I need to plug this. I should have framed it because every time I search with my eyes for these expressions, right? So that will be summation over alpha. Instead of R alpha, I have R capital plus R alpha prime crossed. Okay, you know what? I will erase this. Right. You wrote it down, and I can erase it. Again, in an attempt to save some space. Cross with F alpha external. And naturally, we are getting again two terms, two torques. So the first one, R, doesn't care about the summation, so we'll just sum all external forces, and of course we will get the net external force acting on the whole system. So we'll get R crossed with F. Now I can use external subscript, right? Is that the way I... Yeah, that is just a net external force. And the second one, with the second nothing can be done. This depends on alpha and that depends on alpha, so it will be just summation over the whole system. R alpha prime crossed with F alpha external. Okay, so what's the meaning? Net external force applied, basically this R, it tells us it's a position vector which shows at which point the force is being applied, right? So this force is applied at the center of mass, at the point of center of mass, right? And of course that's the, which way I would call it, net external torque applied at the center of mass. Okay, sounds reasonable, right? So yeah, but the meaning you see, right? So just all the forces, net external force applied at the center of mass. So net external force applied at the center of mass. And here, again, position defines position of the forces. External force acting, for example, on particle 1 or particle alpha, right? Crossed with a position vector, which defines position of that point relative to the center of mass. So that is the external torque acting on particle alpha relative to the center of mass, right? And then we add all those internal torques, right, over the whole system. So that will be the basically like an external torque acting on the whole system relative to the center of mass. And so let me write the what I wrote, just the names. So this will be external torque about the center of mass, of course. Right, so that will be the external torque. And again, you see we have only external torques because only external forces is left, right? Only external torques can change the total angular momentum. Right. External torque about the center of mass. And of course that is, again, external torque applied at the center of mass. Net external torque applied to the center of mass, right? So that is net external torque applied at Cm. Okay, so again, let's just give some, label them. I think this will be just gamma Cm, I think I label it. Let me check it. No, actually I didn't define them. We'll just define this as gamma prime. I thought I gave definitions. No, it looks like I didn't. So just this, let me label it as gamma prime. Okay, so now we are ready to plug it back. Okay, I need this, I need that, I need to erase something. Although maybe I will be able to squeeze it here still. So let me now put a new bullet. Okay, let me put a red bullet because now it's a transition to this equation. Right. So put it in. Okay, L dot equals to gamma external. Okay, so L it's LCM plus L prime. So it will be L angular momentum of the center of mass plus, okay, I can put dot immediately, plus L prime dot. And torque I will just keep for a couple of lines as it is. I'm not going to expand it. I will expand it in a few lines. So external, okay, subscript, not upper script. Right. Okay, all right. LCM, it's our RMV, right? Basically R times P capital. Actually, yeah, I could have remind you, right? So you remember the that first amazing feature of the center of mass when we just introduce it and we grab the definition and differentiate it with respect to time, and we ended up that how we can find the total angular momentum of the system. It's a fake particle with the total mass position at the center of mass. So this is mv capital. It's just the total linear momentum of the system. So that's what I just want to use now. I just don't want to write this mv. It's a p capital, right? P capital. So now I will differentiate this. So it will be d over dt r cross p, and you see bar underneath, it means p capital, right? Total linear momentum of the system. L prime, again, I'm also not going to touch for now, so I will just keep it as it is. I just want to expand it first, this part. So of course it will be r dot cross p plus r cross the rate of change of the total linear momentum, right? Yeah. And again, the rest I will also keep as we have. So plus L prime dot. But now, external torque, yeah, I will write in terms of, I will just use these results. Right, so now external torque I will write explicitly. So it will be R crossed with F external plus, and plus external torque about the center of mass. This plus summation, again, over the whole system, R alpha prime crossed F alpha external. Okay, now I have to get out of that corner. I have to start invading this part of the board. And I think, yeah, I can erase this. I don't think that it's good to have everything so that from time to time you can compare, you can look back, right? So that's why I usually like classrooms with the big whiteboard, so I can erase only, I don't know, a couple of times during the class. Right. Because very often you need to remind, recall, compare, right? So probably I will just go to this point for now. Yeah. So first of all, what is this? R dot cross P. P, it's a total linear momentum of the system, of course. It's M capital R dot. So M capital R dot, basically cross product of two parallel vectors is 0. We've used it already, like it's the third time in the semester we use this, we dump this term calling it 0 because it is 0. So that is 0. Right. Then what's next? This, we are, you remember this, okay, this equation written relative to the inertial reference frame. So the rate of change of the total linear momentum of the whole system equals to the net external force, right? It's that Newton's second law adopted for a multi-particle system. It's the second class, right? So that is, okay, maybe I will write over here. So it is equal to the F external. All right, so this P dot F external. And as a result, look, on this side, we have R cross F external. On that side of the equation, we have again R cross F external. We have no choices. We have to cancel them. They cancel each other, right? So as a result, this and this goes. So the first term 0, and this cancels with that. And what's left? Rate of change of the spin angular momentum, internal angular momentum, and the external torque about the center of mass. Okay, now let me write it down, because now we're getting to basically to the final point, basically to the conclusion. So now, yeah, I'll just rewrite it. So L prime dot equals to summation over the whole system, right? And R alpha prime crossed with F alpha external. F alpha sub alpha external, right? Okay, I will frame it. All right. And so now let's see what we've got, what we've received. To explain all those questions which we asked before, right? How come that we describe, where is my ball? Here. The rotational motion of the ball about the center of mass, it looks like. But look, we started from this equation. This equation is written relative to, okay, now I feel like I needed that picture, right? But you remember, right? This equation was written relative to the inertial reference frame, to the origin O, right? Then what we've done, we haven't changed the reference frame, we haven't changed the origin, we haven't changed anything. We just did some deep Swedish massage to this equation. So we rewrote it, right? So open it up, and then these two terms gets canceled, and this is 0. And then we ended up with this. We haven't changed the reference frame. We are still describing the rotational motion about that inertial reference frame, which was grounded somewhere, right? But now it looks like, by looking at this equation, but this equation, it looks like as what? This is the angular momentum about the center of mass, and this is the net external torque about the center of mass. But again, it looks like as if the origin is at the center of mass. But again, it looks like, because officially sort of we are still in that original inertial reference frame. But because of this lucky derivation, when some terms disappeared, and that equation gets transformed into this, and again, as I said, it looks like as if it was just written relative to the center of mass point. But of course, officially, we're still in the inertial reference frame, grounded somewhere at the original place. So that's why we can say, okay, so we can describe this complicated motion as the superposition of two motions, right? Translational motion relative to some inertial reference frame grounded somewhere, plus rotational motion about the center of mass. Although center of mass can do some bizarre things, right? Accelerate, right? Because, yeah, so who cares that the center of mass accelerates? Officially, you're still at the reference frame, original reference frame, because we haven't changed it. So that's the answer, right? Again, it doesn't mean that solution of the problem, which I already mentioned several times, is going to change. No, it will be still the same solution, right? Translational motion, rotational motion about the center of mass, so all that stuff, all that blah, blah, blah. But we need to understand, we need to realize what actually happens when we do that, right? So that if somebody asks you questions, yeah, you could respond. And so also, right, we can say, right, the rate of course, in order to change the angular momentum about the center of mass, right, only these torques can change angular momentum about the center of mass, right? I mean, these external torques about the center of mass can change angular momentum about the center of mass. And of course, this angular momentum of the center of mass, this can be changed only by this torque, right? Torque when the external forces applied at the center of mass point, right? Okay, so now let me write something about what I just mentioned, and then I will write the last things, that this torque can change that angular momentum, and these torques can change that angular momentum. But first, let me finish this, because it's a very important conclusion. I'm still checking if I mentioned everything. Right. Probably I will write this way. So I will start with this, and then show that that equation gets reduced to this, and so let me write sort of conclusion thus. So L dot, this is the total angular momentum, right? So it's this. So there are no any subscripts, no primes, so it means the total angular momentum equals to net external torque, right? And again, I will write, so it's a about 0.0 that inertial reference frame, inertial RF, right? And then I will write, so it gets reduced, basically this massage, so it gets reduced to this, right? Gets reduced to this, which is rate of change of the internal angular momentum, spin angular momentum, equals to, yeah, this is, that's what I was searching. I remember I used somewhere gamma prime. No, I decided I didn't use it. So anyway, so gamma prime, so which is basically torque, external torque about the center of mass point. Net external torque about the center of mass point. So this is this equation about the center of mass. Right? But again, it's effectively you're still at this point, but now it looks like as if our reference frame was moved to the center of mass point. Okay, so now I can write this. So the center of mass point can accelerate, right? Like in the case of the ball moving, right? Can accelerate, but we can still apply this equation. Can accelerate, but we can still apply. All right, let me write. Okay, let me write this way. L prime dot equals to gamma prime. Apply this equation, but we can still apply this equation because, and it looks like effectively rotational Newton's second law. But again, you remember rotational Newton's second law, strictly speaking, was introduced, and you can use it only in the inertial reference frame. And now all this stuff that you apply it relative to the point which is accelerating, which sounds like bizarre. But of course, there is nothing strange because we're still effectively in the initial reference frame, which is inertial. But we can still apply this equation, since effectively this equation is still relative to the written relative to this original point O. Since effectively this equation it's still written relative to O, relative to that point O inertial reference frame. Right. So that's the explanation, right? So that's why we can still continue using that trick, translational motion of the center of mass relative to some inertial reference frame, plus rotational motion about the center of mass, and we still use this equation, which again looks like rotational Newton's second law, right? Written relative to the written relative to the center of mass. Okay, so I felt like it's important. That's why I digressed to chapter 10, right, in order to clarify that. And yeah, then I mentioned that rate of change of this angular momentum. This angular momentum can be changed only by this torque, right? Net external torque applied to the center of mass. And yeah, and this I already wrote that internal angular momentum can be changed only by those torques about the center of mass. So I will just write, and also which way I wrote it, and also L dot Cm equals to R cross F external. Right. Since this is correct, then of course what's left in this equation, so this net external torque about center of mass, it means that the net external torque about center of mass controls the rate of change of the angular momentum of the center of mass, right? So this we framed, and this we can frame. Whew. All right, so now, and of course we're going to use it. Example, like in a few minutes I will start looking at the example. We will apply this immediately directly. We're going to look at the yo-yo problem. Most of you solved that problem, but it's a direct application of what we just derived. But before we start looking at that, let's just quickly write a few formulas for a rigid object. Again, the book skipped that. He just presented like within half a page, talked a little bit. And then at some point I decided, no, I don't feel like I need to diligently derive those formulas. For a couple of years I derived it, and then I decided, no, it's not worth it. Right? So again, I also was skipping this. Basically, the relationship between the angular momentum of a rigid body, a rigid object, and the angular velocity, right? You remember the tensor, moments of inertia appears, right? And but after a couple of years, I changed my mind. It's like a non-stop process of changing class nodes. You adding something, removing, right? You find something interesting, add, remove, and again, it's a never-ending process. Yeah, I should be able to fit it here, and then I will start example on that part of the board. Right, so let me separate this. Sort of a new bullet. And a rigid body rotating about a fixed axis. So let me write title. So rigid body rotating about a fixed axis. About because now we will start looking at the examples, and rigid objects are going to be everywhere, right? Rigid object is a typical example of a multi-particle system where, of course, connections are rigid, right? Very strong. Rigid body rotating about a fixed axis. A fixed axis. Okay, I will emphasize on fixed axis, and now we need to clarify what does it mean? Which axis of rotation can be called fixed? Because usually the first reaction, first impression, it sounds like a fixed axis. It's something like this. Let's say I have this ball, right? Okay, I need to move this side, right? Sometimes I get confused about directions because in front of me there's a TV, right, where I can see myself on OBS, right? I need that for the green screen effect, right? And everything is flipped, right? So as a result, sometimes confuses me, right? Okay, so fixed axis. Of course, the first reaction you might think of, okay, if I take this, my two fingers, right, and start spinning about this ball about these two fingers, you can think, okay, this is the fixed axis. It's a special case. It's a special case. The definition of the fixed axis is slightly more general. All right, again, it's just a special case. All right, so a fixed axis, it's when the axis of rotation is along the same line, but that line can experience translational motion. For example, let's say this way. Let's look this way. So I'm spinning again, still spinning the ball against around my fingers, right? So the axis of rotation is my fingers, right? But I can move my fingers forward, still rotating the ball, and this is a still example of a fixed axis of rotation. So basically, the axis of rotation must be a line along the same line, and that line still can experience translational motion. Even better example of this case, when you drive the car, right? And if you don't turn, so wheels are spinning, right? And the axis of rotation, the axle, of course, is a line along the same line, right? But of course, that axis of rotation at the same time experience translational motion. So that is the still fixed axis of rotation. But once you turn the car, okay, so now the axle turned, wheels turned, and now axis of rotation turned and turns, and as a result, now of course that is not a case of a fixed axis. So now that line along which axis of rotation is aligned, now it turns, and that is the that axis of rotation is no longer a fixed one, right? Okay, so now let me write that, and the example of the car, that's probably the best example, right? If you drive the car straight, then the axis of rotation of your wheels is a fixed axis, right? Spinning, and axis experience translational motion. But once you turn the car, it's no longer a fixed axis of rotation. All right, so that needs to be mentioned, all right? So direction of axis of rotation is along the same line. Okay, by fixed axis, we mean that the direction of axis of rotation is along the same line, of course, that line which can experience a translational motion also, but the axis itself may translate. may translate. Of course, it doesn't have to be, but if it doesn't translate, it will be a special case, right? It will be still a fixed axis, but it will be a special case of a more general definition of a fixed axis. Okay, so that's we can say it like a definition. And now let me write a few results, which of course we all know, but we need to mention it since it's basic, like, no, not basically, it's a theoretical course, introduction. And of course, everything must be basically derived from the foundations. And so far up to this point, everything was derived. And now I will just pull it up out of the blue. As I said, I used to derive, and then I decided to save time and stopped deriving. Right, so let's assume that we have a rigid object, rigid body, right? So rigid body, right? And let's assume that the axis of rotation is, for example, straight up. That's a given situation, right? So let's assume that this is omega. So this thing is spinning that way. Physical situation given. So we want to describe it. Of course, first of all, we need to introduce coordinate system. Sort of unwritten convention, of course, everyone is trying to align the z-axis along the axis of rotation, right? So axis of rotation is given, and we align z-axis along that direction. Again, sort of like an unwritten convention. So this is z, okay. Slightly displaced, so that is x, that is y. I almost drew a left-handed coordinate system, but you remember what I told you about left-handed. Right, no, this is the right-handed. Okay, and so now, of course, we can derive, but as I said, I'm not going to do it, the expression for the total angular momentum of the rigid object. Of course, it will be total. Right? And for this case, if there is a when the axis of rotation along the z-axis, we're going to have only three components. So I x z times omega. So that is the x component of the angular momentum. And this, product of inertia, right? So this basically gives us x component of angular momentum when the axis of rotation about the z-axis is a line along z-axis. Right? Then the second y component, of course, it will be the product of momentum y z omega. Again, that gives us y component of the angular momentum when the axis of rotation is along z. And of course, the last one, the moment of inertia I z z omega, right? Of course, these are just three elements out of the tensor, right? Because we fixed axis of rotation only along z-axis, right? So as a result, the rest we can dump, right? So this is Ly, and this is L sub z, right? And this Ix and you remember that diagonal elements in that matrix, right, in that tensor of inertia, right, diagonal elements are called moments of inertia. Off diagonal elements are called product of inertia. These are Ixz and Yz are products of inertia, and these are one of the diagonal elements. It's called moment of inertia. So these are Yz products of inertia. Let me use plural products of inertia. And of course, Izz, of course, moment of inertia. Right. And of course, if a body symmetrical relative to z-axis, then of course these Ixz and Iyz will be zero. So if a body is symmetrical, it can be easily shown because when you derive this, of course, you can look at the expressions for Ixz and Iyz. You see that if there is a symmetry, terms will be cancelled, right? A body is symmetrical, then, of course, Ixz equals to 0 and Iyz will be equal to 0. Basically, when you go to the garage to have your wheel aligned, what do? They just put it on a spinning system, right, and start adding some small objects, right, so to change the distribution of mass along, right? So basically, they're trying to make your wheel as symmetrical as possible about the axis of rotation, so that this and this will be 0, and so that angular velocity will be aligned along the angular momentum, so that there wouldn't be any wobbling. Because right now you have angular velocity along z direction, but you have x, y, and z component of the angular momentum. So it means that if you have an asymmetrical object, of course, there will be lots of wobbling, right? But once you remove this and that, omega will be along L, and you will have a smooth ride. So then, this is 0, and of course, the formula, of course, which we will need basically because of that formula, I digressed over here. And of course, L will be equal to I omega. Of course, it will be Izz omega, right? But there's no point of adding those subscripts if you have that only. Right, and the next equation, I feel even worse, right, giving it. Kinetic energy associated with rotational motion, because we haven't even started introducing the energy approach, and now out of the blue I just dump, because at some point we will need it, not now, but in a few classes, right? And of course, kinetic energy. Pretty much, I think maybe at the end of the next class, we will start introducing energy approach, because right now we brought all the tools which we needed to describe complicated motion, translational motion, rotational motion. So now we just need to look at a couple of examples, and that's it, right? And then I will explain why we need the energy approach. So kinetic energy, and of course kinetic energy, T will be equals, of course, 1/2 Izz omega squared. Of course, for symmetrical case, I sub zz omega squared, right? Okay, I will frame it this way. Okay, it looks like we will not be able to finish the example. And as I told you, we are going to look at yo-yo problem, right? You've solved it. I'm sure that you solved it in the past, but now we need to solve it diligently using what we just discussed, right? Okay, at least maybe I will draw the picture so that a few minutes I can save next class. Let me check if I need. Yeah, of course I need all that, but I also need space to write new stuff. That's why I'm so happy when I realized that classroom where I teach classical mechanics has lots of whiteboard. In that case, it's so pleasant to work. So, a yo-yo problem, a falling yo-yo. Right. Very popular example. Right, so of course, it's basically yo-yo is a disc, cord, okay, string is attached, wrapped, right, and it just goes down, right? And so we need to describe that motion. But by description, I mean we will find acceleration and, of course, tension. It's a classical example, right? So let me start with the pictures. So let's say this is the ceiling. Right. What is given? Just mass. Mass We can introduce radius, but I don't think a radius is not important, right? Just a mass. Right. Then the chord. You know what? Let me first draw the yo-yo. Sometimes I use plates in order to draw bigger. I have here a collection of plates, some circular objects, so I can draw circles of different diameter. Right, and that is the chord. Right. Okay, so that is our yo-yo. And first of all, it's Newtonian formalism. We need to introduce coordinate system. Of course, that must be inertial, right? Okay, so it makes sense, of course, to ground it at this point, right? So, and down, it will be my y-axis. This will be x-axis, and z-axis must be in order to have right-handed coordinate system. Okay, so this will be z-axis, right? Okay, and actually, the class is already like 2 minutes over the class time. So yeah, we will. I will just again draw the picture before the class. And so from this point, what we have to, we need to write down the fundamental equations which we need to use in order to describe this motion. And of course, we know that is. Translation, I mean, the Newton's second law for multi-particle system, and then rotational Newton's second law for multi-particle system, right, which we just discussed. And we will just need to apply them carefully for this.